Okay, so we will discuss a few problems related to classical thermodynamics as well as classical statistical mechanics that we discussed so far. So, the first problem is calculate the final volume of 1 mole of an ideal gas initially at 273 Kelvin temperature and 1 atmospheric pressure. If it absorbs 1000 calorie of heat during a reversible expansion. The problem is the calculate the final volume of 1 mole of an ideal gas initially at 273 Kelvin temperature and 1 atmospheric pressure if it absorbs 1000 calorie of heat during a reversible expansion. So how to solve this problem? Okay. So rather we can say that okay, so this is reversible isothermal expansion if we consider. Okay. The problem is slightly modified now. The calculate the final volume of 1 mole of an ideal gas initially at 273 Kelvin temperature and 1 atmospheric pressure if it absorbs 1000 calorie of heat during a reversible isothermal expansion. Okay, so we have here how to solve this. So we have ideal gas as well as isothermal process. Right? And we know for ideal gas the internal energy depends only on temperature. So for isothermal process du equals to 0 for an ideal gas. And from first law of thermodynamics we know du is del q, process is the reversible one, del q reversible plus del w reversible. Since du is 0, so we can write del q reversible is nothing but minus del w reversible, and this is p dv, and we need to calculate q reversible. Q reversible is nothing but, if we integrate it, we get a naught p is a naught t and then ln V2 by V1, where V2 is the final volume and V1 is the initial volume. So what is the initial volume? So initial volume V1 is nRT by P. So it gives us V1 is N is number of mole is 1 here, R is 0.082 in liter atmosphere unit, and temperature is 273 and pressure is 1 atmosphere here. So you get this V1 is in liter. Okay. So we get the value of V1 here, and we need to calculate V2. Okay, so Q reversible again is 1000 here. Okay, and N is 1, R is 2 in calorie unit, temperature is 273, ln V2, and then V1, the value we are getting here, we need to substitute here. Okay, this V1 we need to substitute here, and then we need to calculate V2. If we do it, we get approximately 140 liter. Okay, so this is how you do it. Okay, so first thing we need to do is we need to, since we consider ideal gas here, so an isothermal process du is 0, there is no change in internal energy for this process, and if we substitute du equals to 0, then we get del Q reversible is minus del W reversible, and del W reversible we know P dV. So if we substitute that, we get minus P dV, we substitute that, then we get P dV here. So we know Q reversible is 1000 calorie, and here R is 2 and temperature is 273 Kelvin. Okay. Now one thing you must be cautious here, while putting or while using the value of R, you need to consider, we consider two different R values here. One is in liter atmosphere unit while calculating the initial volume, and while calculating the final volume here from the first law of thermodynamics, we use the unit of R in calorie. Okay. So this is a very simple problem, problem number 1. Next we consider a little or slightly difficult problem. Okay. So it says, problem number 2 we discuss now. For a certain reaction, at constant pressure, delta G is given as minus A plus B times T and ln T, log of T, where A and B are constants and T is absolute temperature. And we need to calculate change in enthalpy or delta H. Okay, this is a very simple problem. We will use here Gibbs-Helmholtz equation, okay, because that relates delta G and delta H. Okay, like we know here the given delta G is minus A plus B times T ln T, or delta G by T is minus A by T plus B ln T. Now, if we differentiate delta G by T with respect to temperature at constant pressure, we get, and right hand side is nothing but minus delta H by T to the 2, and it gives us delta H is minus A minus B times T. Okay. This is a simple but very nice problem. Okay. So delta G was given and we were asked to calculate delta H. Since delta H related to delta G is related to delta H by Gibbs-Helmholtz equation, we are applying Gibbs-Helmholtz equation in this problem to calculate delta H from the expression of delta G by differentiating delta G by T with respect to temperature at constant pressure. Okay. So we will do another simple problem. Problem number 3 is 1 mole of a gas obeying the equation of state P times V minus B equals to RT undergoes a change from the initial state T1 V1 to a final state T2 V2. What is the value of delta S that we need to calculate? Assume Cv is x plus y times t plus z times t to the 2. Okay, so here the problem says 1 mole of a gas obeying the equation of state. So, for the gas, equation of state is given P V times minus B equals to RT undergoes a change from the initial state T1 V1 to a final state T2 V2. What is the value of delta S, or change in entropy we need to calculate? And here Cv is not independent of temperature, rather Cv is dependent on temperature. And Cv, the expression for Cv is x plus y times t plus z times t to the 2. Okay. So, we already discussed what would be the entropy change when both temperature and volume are changing. Okay. So, entropy change in terms of V and T. So, we know del Q reversible is TdS is Cv dt minus plus Pdv, right. So, we get ds is Cv by T dt plus P by T dv. Okay. So, what is the value of P here? So, the equation of state is, so the gas equation of state is P times V minus B is RT. So, it gives P is RT by V minus B. So, now we will substitute the value of Cv and P into equation 1, and then we will do the integration. And if we do the integration, we get the change in entropy. So, we have ds equals to Cv by T dt plus P by T times dV. Now, what do? We substitute the value of Cv and P in this expression, and we get ds is x plus y times t plus z times t to the 2 by t times dt, and P is our RT by T times V minus B times dV. So, this is ds. Okay. So, if we do the integration, and the value of S1 and S2 are the initial and the final entropy, we do the integration, we get integration S1 to S2 ds equals to integration T1 to T2 x plus yt plus zt to the 2 yt times dt times dt plus RT by T times V minus B times dV, and volume changes from V1 to V2. So, if we do it, we get delta S is x ln T2 by T1 plus y T2 minus T1 plus z T to the 2 minus T1 to the 2 by 2 plus R ln V2 minus B by V1 minus B. So, this is the answer. So, if we now integrate it, so delta S is again is 2 is function of T2 minus T2 and P2 minus S1, which is a function of T1 and P1. So, delta S is nothing but S2 minus S1. So, delta S is x ln T2 by T1 plus y times T2 minus T1 plus z T to the 2 minus T1 to the 2 by 2 plus R ln V2 minus B by V1 minus B. So, this was our problem 3. Next, we will discuss another problem. One analytical problem. Okay, so it is not numerical. So that problem 4 is del Cp by del P equals to minus T del 2 V by del T to the 2 dP. So, this is an analytical problem, as I said. So, we will start with Cp. Okay. How do you solve it? Okay, so, we know Cp is del Q by del T at constant pressure, right, and this is nothing but del T del S by del T at constant pressure. Okay. So, del Cp by del P is T del 2S by del T to the 2 times del T sorry del 2S by del T del P, right. So, this is del Cp by del P. Now, we need to prove del 2S by del T del P equals to minus of del 2V by del T 2 at constant pressure. Okay. So, from Maxwell's relationship, we know del V by del T at constant pressure is nothing but minus del S by del P at constant temperature. So, it gives us del 2V by del T 2 at constant pressure is minus of del 2S by del T del P. So, we can prove that Cp del Cp by del P is nothing but minus T del 2V by del T2 at constant pressure. Very easy to prove, only thing we need to remember Maxwell's relation. So, this is proved. So, the next problem is we consider, so this is problem number 5. This is very interesting problem. The volume of a system consisting of an ideal gas decreases at constant pressure So, the volume of a system consisting of an ideal gas decreases at constant pressure. As a result, the temperature of 1.5 kg of water in the surroundings increases by 14.2 degrees Celsius. Calculate QP for the system. And it is given that Cp of water is 4.18 joule per gram per Kelvin. Okay. So, this is very interesting problem. It says the volume of a system consisting of an ideal gas decreases at constant pressure. As a result, the temperature of a 1.5 kg of water in the surroundings increases by 14.2 degrees Celsius, and we need to calculate heat change for the system, and Cp of water is given. Okay. How do you solve this problem? So, QP system is nothing but minus QP surroundings, right, and or we write minus QP system is QP surroundings, okay, and this is nothing but AMCP delta T, right. So, we get QP system. So, M is the mass of water here. So, this is in gram unit, and then Cp of water is given times 4.18 joule per gram per Kelvin, and delta T is also given. So, times 14.2 Kelvin. So, QP system is nothing but minus of 89. We have a minus, we have minus QP system. So, QP is minus 89.034 kilojoule. Okay, so this is the answer. Okay, so how to do it? So, you have a system, okay, and it has ideal gas. So, the volume of the system decreases, okay, and as a result, the temperature of water which is present in the surroundings increases, okay, by 14.2 degree Celsius. And what is the mass of water? Mass of water is 15.4. Okay. So, heat is getting transferred from the system to the water present at the surroundings. That is the main concept for this problem. Next, we consider another simple problem. A typical resting person hits the surroundings at a rate of about 100 watt, where 1 watt is 1 joule per second. Estimate the entropy the person generates in the surroundings in the course of a day at 300 Kelvin temperature. So, this problem says a typical resting person heats the surroundings at a rate of about 100 watt. Okay. So, 1 watt is 1 joule per second. Estimate the entropy the person generates in the surrounding in the course of a day at 300 Kelvin temperature. So, the person is heats the surroundings. So, first the heat is getting transferred from the system is a person here, system to the surroundings. Okay, and how much heat it is transferring? 100 watts means 100 joule per second. Okay. So, what is the heat is transferred from the system to surroundings. So, Q, if we say Q surroundings, and if we consider the process is reversible one, this heat transfer process. So, you can write Q reversible surroundings is 100 joule per second, and in a day we have 3600 times 24 second. Okay. And what is temperature here? Temperature of the day is 300 Kelvin. So, the entropy change of the surroundings is 100 times 3600 times 24 by 300 joule per Kelvin. So, this is in joule unit, Q reversible. Okay. So, we get delta S surroundings is 36 or 1200 times 24 joule per Kelvin. This is simple yet interesting problem. Okay. Next, we consider a problem which is very simple one. This is problem number 7. Suppose 5 moles of an ideal monatomic gas at an initial temperature of 298 Kelvin and pressure of 10 atmosphere is expanded adiabatically and reversibly until the pressure has decreased to 1 atmosphere pressure. Calculate the final volume, final temperature, the internal energy, internal energy change, the enthalpy change, and the work done. Okay, so this is a textbook problem kind of. So suppose 5 moles of an ideal monatomic gas at an initial temperature of 298 K and pressure of 10 atmosphere is expanded adiabatically and reversibly until the pressure has decreased to 1 atmosphere. We need to calculate the final volume, final temperature, the internal energy change, the enthalpy change and the work done. Okay. The problem is as I said, it's very straightforward one. Okay, so what we need to do, what the information provided here are number of moles, N is number of moles, equals to 5, initial temperature T1 is 298 Kelvin, initial pressure P1 is 1 atmospheric pressure, final pressure P2, initial pressure is 10 atmospheric pressure and final pressure is 1 atmospheric pressure. We need to calculate, and Cv for monatomic gas, Cv is 3/2 R, Cp is for ideal monatomic gas, Cp is 5/2 R. So, Cp by Cv, which is a gamma, is 5/3, and we need to calculate first final temperature T2 is what. So, these are the information we have. Okay. So, number of moles 5, initial temperature 298 Kelvin, initial pressure 10 atmosphere, final pressure 1 atmosphere, and we need to calculate final temperature, which is defined as T2. This, and we know the for ideal monatomic gas, Cv is 3/2 R, Cp is 5/2 R, and Cp by Cv, which is a gamma, and the value of gamma is 5/3. Okay, so the process is adiabatic process and adiabatic reversible process. Okay, so the process, so this is an adiabatic reversible process. And we know for adiabatic reversible process, P1 V1 to the gamma is P2 V2 to the gamma. And if we substitute the value of V1, here we get P1 to the 1 minus gamma times T1 to the gamma is P2 to the 1 minus gamma and T2 to the gamma. So, we get T2 by T1 to the gamma is P1 by P2 to the 1 minus gamma. And if we substitute all this value, we get T2 is 118.76 Kelvin. So, this is the final temperature T2 we have calculated. So, once we get T2, we can easily calculate. We know final pressure, we know number of moles, we can easily calculate final volume. Okay. So, final temperature we have obtained is is 118.76 Kelvin, and V2 is nothing but nR T2 by P2. So, V2 we get 5 R is 0.082 in liter atmosphere unit, T2 we have just obtained 118.76 and P2 is 1 atmosphere, right. So, P2 is 1 atmosphere, and if we calculate this, we get V2 is 48.69 liter. Now, next thing we need to calculate W, delta U and delta H. Now, for adiabatic process, Q is 0, so delta U is W. Okay. So, and delta U is nothing but N CV delta T. N is 5, CV is 3 by 2 times R if we substitute in joule unit, we can write R is 8.314 and delta T, T2 minus T1, so 118.76 minus 298. If we calculate delta U is minus 1176.51 joule, and which is nothing but W. So, W is also minus 1176.51 joule. Okay. So, we got both W and delta U. Next, we need to calculate delta H. So, delta H is very easy to calculate. Delta H is NCP delta T. So, N again 5, Cp is 5 by 2 times R and delta T is T2 minus T1. Okay, so, if we substitute all these things, we get delta value of delta H is 18,627.52 joules. So, this is very easy and a textbook problem. Okay. Next, we consider let's see if we can calculate something interesting next. So, next problem is again analytical problem. A certain system is found to have Gibbs free energy given by where A and R are constants. We need to find the value of Cp. So, okay, so the problem says a certain system is found to have Gibbs free energy given by G, which is a function of pressure and temperature, is RT log of AP by RT to the 5 by 2, where A and R are constants, and we need to calculate the value of Cp. So, how do we proceed? Okay. So, G, so we have G is RT ln AP plus 5 by 2 RT ln RT. Okay. So, we get G, which is function of P and T is RT ln A plus RT ln P plus 5 by 2 RT ln R and we know del G by del T at constant pressure is minus S. Okay. That we discussed in one of our class. Okay. So, this relationship. Okay. So, we have the value of G here. Now, if we differentiate G with respect to T keeping pressure constant, we get del G by del T at constant pressure. The first term gives us R ln A, the second term gives us R ln P, the third term is 5 by 2 R ln R, and the last term gives us 5 by 2 R ln T plus 5 by 2 times R, T times 1 by T. So, if we solve it, we get del G by del T at constant pressure is R ln AP plus 5 by 2 R ln RT plus 5 by 2 R. So, we get S, value of S. So, S is minus R ln AP minus 5 by 2. Oh, okay. So, there is a mistake here. So, we have a minus sign, because if we take log, we get here minus. So, we have minus signs there, and then we have minus sign here, here and here. Okay, so we get minus sign here and here. So, we get S is minus R ln AP plus 5 by 2 R ln R plus 5 by 2 R ln T plus 5 by 2 R. So, this is S. Now, Cp is del Q by del T at constant pressure, or we can write Cp dt or dq is nothing but Cp times dt, dq by T is Cp dt by T. So, we get Tds is Cp dt, or Cp is del S by del T at constant pressure times T. So, this is how we can calculate Cp. So, Cp is nothing but T times del S by del T at constant pressure. Now, we have the value of S. So, what we need to do now? We need to differentiate S with respect to temperature keeping pressure constant. So, if we do it, we get del S by del T at constant pressure. The first term from here, first term gives 0, second term also gives 0, and third term gives us 5 by 2t, 5r by 2t. Okay, so, we get del S by del T at constant pressure is 5r by 2t. So, Cp is T times 5r by 2t. So, this gives us Cp is 5 by 2r. So, here what we did, from the expression of G, we basically first calculated entropy S by differentiating the expression of G with respect to T at constant pressure, which gives us minus S. Once we get S, then we can calculate Cp from del S by del T at constant pressure. The last problem for today's class we have now, we will discuss is starting with A is equals to U plus PV, so that del U by del T at constant pressure is Cp minus P del V by del T at constant pressure. This is just a one step problem rather. So, H is U plus PV. So, dH is du plus P dV plus V dP. So, del H by del T at constant pressure is del U by del T at constant pressure plus P del V by del T at constant pressure, and the third term is 0, and del H by del T at constant pressure gives us Cp. Cp is del U by del T at constant pressure plus P del V by del T at constant pressure. So, we get del U by del T at constant pressure equals to Cp minus P times del V by del T at constant pressure. So, this is a very simple problem, and we can really prove it. Thank you.